All right, let's knock out this last example real quick. There's some people in my building doing smoke alarm testing, so if you hear a faint beeping, that's where it's coming from. But I really want to knock out this video, so I'm not going to wait to do it until they're finished. So let's go ahead and take a look. We've got an RL circuit with an initial condition. We've got 5 milliamps flowing through the inductor initially, which basically means we have 5 volts here, 0 volts here. So there's 5 milliamps flowing through the resistor and 5 milliamps flowing through the inductor because they are in series. That's the initial condition. And so we basically want to model this circuit in the S domain and determine the time domain expression for the current flowing when we transition from 5 to 0 here, right? And so again, I'm modeling this source in the S domain. It's going to come out to 5 over S minus 5 over S, which just goes to 0. And so I'll model that as a short, basically just nothing there. My resistor here. My inductor is obviously SL, but I need to model the initial condition as well. And in this case, it's going to make sense to model it as a voltage source since we're looking for the current here in this circuit. So I'll call this R, and then I need to model this as L times the initial condition for the current, which in this case is 5 milliamps, okay? Please forgive me again for the beeping. I can hear it. I'm sure you can as well. And so we want the current flowing through the inductor, which is this direction. Let's call it I of S. And so we've got this drop here, and we can write a KVL expression for this loop. So I'm going to write minus I of S times R, minus I of S times SL, and then plus L times 5 milliamps, okay? And so we can say that that's equal to 0. We can keep the L times 5 milliamps on one side and add the other two terms over. So we're going to get I of S multiplied by R plus SL here. Yeah, this looks right. And so now I can isolate I of S. I get I of S is going to be equal to L times 5 milliamps divided by R plus SL. What I'm going to want to do first is divide both the top and the bottom by R so that I can get L over R times 5 milliamps over 1 plus SL over R. And then what I'm going to want to do is multiply the top and the bottom by R over L. So I multiply top and bottom by R over L, and that's going to give me 5 milliamps divided by S plus R over L, or in this case, you could say 1 over L over R if you really wanted to, just to keep it in terms of stuff that we've already seen. And now very easy to get this into the time domain. Again, it's just going to be I of t is equal to 5 milliamps multiplied by e to the minus t over L over R, and that is our de-energizing current expression for the inductor. Of course, this is going to be multiplied by u of t so that we know that it is sorry, I have a hair on my screen, so that we know that it's only valid for time t greater than or equal to 0. So we can rewrite this as e to the minus t over L over R for t greater than or equal to 0. And that does it. All right, so we're all done with EE221. If you made it this far, congratulations. This is super exciting for me. It should be super exciting for you. If you have any questions about any of this material, please let me know. I know that it's not easy stuff. The math in this class is definitely heavy, but I'm very glad that we made it this far, and we'll see you guys soon for the final exam. And yeah, take care.